This lecture is going to cover projectile motion. We're still on section 3.5. We're going to finish it up by talking about what projectile motion is and how we break it down, or how we approach all of the concepts that are held within projectile motion. First thing that we're going to take a look at is the definition of projectile motion. So projectile motion is just motion in two dimensions near the Earth's surface. So you can consider somebody throwing a golf ball, batting a baseball, kicking a football, a speeding bullet. All of these are objects traveling through the air in a horizontal direction, but we know because they're in free fall they're going to hit the ground. We took a look on Tuesday at an example of projectile motion with our cannon. So when we do projectile motion, we want to start by focusing on the situation that takes place near the surface of the Earth so that we know what the acceleration due to gravity is going to be. And we want to make sure that we consider situations where we can ignore air resistance, because we want to start by being able to solve the simplest type of problems. If we do that, then we're channeling our good friend Galileo, who came up with the first correct description of projectile motion as vectors. Aw, isn't that sweet? Mr. Galileo, you are a smarty. Okay, so if we're going to take a look at projectiles, we need to analyze the horizontal and the vertical motion separately. It's the only way to do it. And it makes sense because position, velocity, and acceleration are all vectors, and vectors can be broken down into their components. So let's take a look at an example velocity. All right, let's consider an example velocity of, we'll say, all right, we will make this velocity vector, let's say, I want to make it a really funky number, like 22.86 meters per second. And we'll say that that velocity vector is, let's stay true to form here. I want to say it's about 35 degrees above the horizon. All right, in reference to the positive x-axis. All right, so if this is our velocity vector, we can analyze the horizontal and the vertical motion separately. All we need to do is set our axes. And when we're looking at projectile motion, we want to make sure to always set our horizontal and our vertical axes so that horizontal is our x-axis and vertical is our y-axis. So I'm going to do just that. I'm going to say that, all right, this is our y-axis, and this is our x-axis. And once I've set my axes, I can now find the x and the y component of my vector. And one thing that I know is I know that I want my x-axis to be my horizontal component, so I'm going to call that Vx, the x component of this velocity. And my y component, Vy. And I'm going to get rid of that because I like my drawings to be accurate, but I mess up sometimes. So now I know that this velocity vector is made up out of the component Vx added to the component Vy. Vx plus Vy added vectorially will equal the overall vector V. And so we're going to name this overall vector V. So what I want to know is I want to know what Vx is and I want to know what Vy is, so I'm going to use my SOHCAHTOA. I'm going to use my relationships. And I know that the sine of 35 degrees is going to equal Vy over V. So that means that Vy is going to equal V sine 35. So Vy is going to equal 22.86 meters per second times the sine of 35. Vx is going to equal V times the cosine of 35. By this same relationship, the cosine of 35 equals Vx over Vy. And when I solve for this problem, Vx is going to equal 22.86 meters per second times the cosine of 35 degrees. So I can check. I can say that my Vx vector is going to equal 22.86 times 35 cosine, or 18.72 meters per second, 18.73 meters per second. And my Vy is going to equal 22.86 times sine of 35, or 13.11 meters per second. Alright, so these are the x and the y components, and I can check my work. I can make sure that I did this correctly, because adding these together vectorially means that v will equal the square root of 18.73 squared plus 13.11 squared. So let's check it out. Hey, look, that equals 22.86 meters per second. So I've been able to just prove that vector components work through those relationships. This works for breaking down any one vector. It also works for adding multiple vectors together. So let's take a look at adding multiple vectors together. So we could say that Benny looking extra creepy today. First, he levitated with a velocity of 10 meters per second at 10 degrees above the horizon. And then Benny levitated with a velocity of 22 meters per second at, we're going to call that 50 degrees above the horizon. And so what we're going to do is we're going to figure out what his overall velocity was, or his average resultant velocity. Alright, and we're going to do that by adding together the x and the y components of these two vectors. Alright, so we're going to set our x and our y axis, and I can set two different axes as long as they're parallel, right, both in the vertical direction. Those are our y axes, and our x axes And then I'm going to find my components of each individual vector. So I'm going to call this right here. I'm going to call this one velocity 1. So this will be the x component of velocity 1. This is going to be velocity 2. So this will be the x component of velocity 2. Alright, here's going to be the y component of velocity number 1, and here's going to be the y component of velocity number 2. And you can clearly see that if I added Vx1 plus Vx2, I would get the total in the x direction, or the x component of the resultant velocity. And likewise, if I added Vy1 plus Vy2, I would get the total velocity for the resultant velocity in the y direction. And so that's exactly what we're going to do. We're going to use these to break each vector down into its components and solve for resultant velocity. So I'm going to use those relationships that I know. And I know that the x component of velocity number 1 is going to be v1 cosine of 10 degrees. And the x component of the second one is going to be v2 times the cosine of 50 degrees. And that will give me my x component of my resultant velocity. And over here, it's going to be v1 sine of 10 degrees plus v2 sine of 50 degrees. That will give me my velocity in the y direction. Plugging in the value of the first velocity vector and the second velocity vector gives me, for the first problem, 10 meters per second times cosine 10 plus 22 meters per second times cosine of 50. And down here, 10 meters per second times sine 10 plus 22 meters per second times sine 50. And I solve. And how you solve these is really up to you and your comfort level. So that's going to be 9.85 meters per second plus I'm going to keep more significant figures than that, 848. And then it's going to be plus will equal 23.99 meters per second. And that was actually only going to have two significant figures, so that's going to be 24 meters per second. And then down here, I'm going to do sine of 10 times 10 meters per second plus the sine of 50 times 22 meters per second. And I'm going to get 18.59 meters per second. Two significant figures is going to be 19 meters per second. So here I have found the x component of the resultant velocity and the y component of the resultant velocity. So what I've actually found is I've found this and this. Alright, and if I add these together vectorially, I will get my resultant vector. And so I'm going to do just that. And I get 31 meters per second. And that's going to be the magnitude of the resultant velocity. But now we need to find the angle of the resultant velocity, and the angle of the resultant velocity is going to be given by the ratio of the x and the y components. So I can use the relationship tangent theta will equal v in the y direction plus v over v in the x direction. So that means that the actual angle is going to be inverse tangent. Sorry, I'm doing my work out of screen. Inverse tangent of y direction was 19 meters per second. X direction was 24 meters per second. So 19 divided by 24, inverse tangent. The theta was 38 degrees above the horizon, so we'd see at 38 degrees above the horizon. So you can see that you can use vector components to break a problem down until you get your overall answer. We used the x and the y component of two separate velocity vectors to find the overall magnitude of the resultant velocity and its angle. So moving on through, we're going to go back to talking about how breaking objects down into their how breaking motion down into its x and y components actually allows us to solve for projectile motion. So what I'm going to suggest is let's look at a tiny ball, which is another way of saying let's look at a spherical cow ball, a ball that we can neglect all motion besides its translational motion. And we're going to talk about that ball being projected off of the edge of a table. And what we're actually going to consider is we're going to consider two spherical cow balls. So but to compare, we're going to do just like we did in class. And we're going to talk about one that has an initial horizontal velocity in the x direction and one that just falls down vertically. Or in other words, it doesn't have velocity in the x direction. So here are those two balls. And like we said, one of them has no velocity whatsoever in the x direction, right? So for this ball, our initial velocity in the x direction is going to be 0. However, the other ball was rolled over the edge of the table. So for that ball, its x velocity was something other than 0. So what we know is, let's start with what we're most comfortable with, and that's a falling object. This falling object, right, we also know that its velocity in the y direction initially is 0. It's just falling down. Alright, so that means that it starts out, acceleration starts working on it, right, and it's going to fall down. So it starts out with no y velocity, but with each increase in time, its y velocity increases, right? So here at point 1, it has some y velocity. Here at point 2, its y velocity is larger because it's accelerating due to gravity, and larger and larger and larger. So it actually is moving the fastest when it makes it to the bottom of the table. We know that also initially, right, so we'll call this point 1, point 2, point 3, and point 4. And we know that for each of those points, Vy does not equal 0. Vy1, Vy2, actually Vy2 is there, Vy3 is here, and Vy4 is here. We know that that value is some value greater than 0. And likewise, here, when a ball falls off of the table, it follows this projectile path motion like this. Right? It just follows some parabola. And like we viewed in class, one of the things that we know is that whether an object is projected horizontally or just dropped, they hit the ground at the same time. So we can also infer that that means that the path that they fall by is equally exact. Which means that we could also say that the initial y velocity of the projected ball is some zero value. And we also know that because they're both falling due to gravity, right, that y velocity increases due to gravity the whole way down. Alright, so we know that that y velocity should be the same for both the falling ball and the projected ball the whole time. We know that that relationship is equivalent. What we need to figure out is we need to figure out what that x velocity is the whole time. Alright, because if we consider Galileo's idea about the projected ball, then we know that the velocity of the ball is a result of its x velocity moving in the horizontal direction and its y velocity falling due to gravity, and that means that its resultant velocity would be the vector addition of Vx and Vy all the way across the path. Right? And that we know would be true in any situation. So this is what we're considering. Right? We can compare exactly an object that's falling in free fall to an object that is experiencing projectile motion. The thing that's connected between the two of them is their y velocity. If they're both in free fall, then their y velocity at any point in time, at any second along the fall, would be exactly the same, which means we would use the exact same kinematic equations. The only difference is that this ball also has some x velocity, and because it has some x velocity, its overall velocity is going to be a resultant vector, the addition of the Vx and the Vy together, and that's what actually causes that projectile pathway. So a problem-solving tip is whenever we can in a projectile motion problem, we like to set the initial time to 0, the initial x position to 0, and the initial y position to 0, and then we just calculate our displacement and time change as whatever it is at that final position that we're considering. So now that we've considered that situation, we can look. And one of the things that we noticed is that on a projectile pathway, at any instant, the overall velocity, the resultant velocity that's a result of the fact that it's moving in the x direction and the y direction, that velocity is tangent to the path. Right, so that's saying that if a ball is following some projectile path, right, the velocity at any point in time along that path, we'll consider here, the velocity would be a tangential line there. The velocity here would be a tangential line. The velocity here, a tangential line. All right, so that's always going to be the resultant velocity, the velocity that's the result of its x and its y motion. That's always going to be true. So as long as we set our axis so that y is always vertical and x is always horizontal, here, look at this. And we could do either a separate x-axis for each one that we want to consider, which is sometimes helpful for visualization in these problems. or we could set one axis. But we do know that the y-axis is vertical and the x-axis is horizontal. And we can treat horizontal and vertical velocities as independent, right? We know that for each of these instances, right, it's going to be moving, its y component is going to be because of gravity, right? Which means that up here it doesn't have a y component, because if you were going to do the y component of that, you'd find that y equals 0 along that axis. So we know that the y component is due to acceleration from gravity, and the x component is due to something else. So now that they're independent, we can apply kinematic equations to solve for the x and the y components of the motion. I want to examine the y component of the motion first, because we can compare it to free fall, which is current and fresh for us. So for an object that's just rolling over the edge, an object that's just shot straight out, right? At the initial time, it only has an x component to its velocity, so its initial y velocity is going to be 0. Right? So especially, like, take a look at this situation. I'll look at the situation of a ball rolling off of a table. I'll look at the situation that we saw in class where we shot the cannon and the cannon was perfectly level with the horizon. Right? The initial velocity is 0. If that's true, we also know that it has an acceleration due to gravity of 9.80 meters per second squared. All right, that acceleration from velocity comes from the fact that the object is in free fall. All right, because of gravity, we know the ball will hit the ground eventually, or it will hit something, some sort of a surface between the ball and the ground. We set up the axis. Y is and we have our y-axis like this, so we're going to say that up is positive and down is negative, so that gives our acceleration due to gravity a value of negative 9.80 meters per second squared. This is going to be convenient for projectile problems. And in our y, we know that at any point in time, since v0 is 0, applying our kinematic equations, right, vy equals negative gt, where we have replaced, this is the equation vy equals v naught y plus at, where we substituted g for the a, and we said that this value is 0, and it gave us negative because g is negative. So our velocity at any point in time is going to be the relationship between time and gravity, and it's going to be a negative value. Our y velocity is going to be in the downward direction, moving down on the axis. We can also consider position, right? And position, we get this from the equation where since vy is 0, we eliminate that, and since g is our acceleration and it's negative, we get the equation 1/2 gt squared. That means that these are for free fall and for projectile motion. In the y direction, or falling vertical, our kinematic equations that we can use to solve are vy equals negative gt and y equals negative 1/2 gt squared. And as long as these things are true, right, down is negative, and this is the y-axis, and g equals 9.80 meters per second squared, and it's a negative value because it's going down, these equations are going to be true every single time. And so that means you could solve for anything in a projectile motion problem in the y direction using these two equations. In the x direction, the horizontal direction, right, what do we have to consider? Well, in the horizontal direction, gravity doesn't act. Sorry, the lights went out. Right, in the x direction, gravity is not acting. Gravity is a downward acceleration. As long as there's nothing causing the object to speed up or slow down, acceleration is going to be 0 in the x direction, which means we have uniform motion. Right? So horizontally, acceleration equals 0, and we have uniform motion. And if we have uniform motion, then that means that the velocity is constant. That means that the final velocity in the x direction will be the same as the initial velocity in the x direction, which means that this is the only equation that we're going to need. For position, it will always equal whatever the initial velocity was times time. Right? And that comes from the relationship of velocity on a uniform motion situation is going to be equal to the displacement over time. And this equation is the same equation. And it's the only equation that we need for uniform motion. Alright, so that means that at any instant we can find velocity by adding the Vx and the Vy components. So that means that in a situation where you have some sort of falling object that was projected, we can say that this object was projected from, we'll say, a height of 8.00 meters, right? And it was projected with a velocity of, we'll say, 10.0 meters per second that way. So we could consider if this is the pathway that the object takes, we could find what is its velocity at the instant it hits the ground. Well, its velocity vector would be some value like that, and we only have two values, but what we do is we do know that in order to solve for that, we're going to need to find both the x component and the y component of the velocity. And we can do that because we know that in the vertical or y direction, Vy is going to equal negative gt. And the position is going to equal negative 1/2 gt squared. In the horizontal, right, x equals v naught xt. Sorry, I'm out of screen again. So we know that these things are true. So we can solve for the final velocity at the ground. We can also solve for how far away it hit. So let's take a look at how to break this problem down. Well, the first thing we need is, in order to find the velocity in the y direction, we're going to need time. The only way to find time is through its relationship with the position. The ball was launched from 8 meters above the ground. So y is going to be 8 meters, and acceleration is going to be 9.80 meters per second squared. So we can use this to solve for time. Time is going to equal the square root of 2y over g, which is going to be equal to the square root of 2 times 8.00 divided by 9.8 meters per second squared. So this object fell for 2 times 8 divided by 9.8 square root, 1.2 seconds. Now, from this time, we can now figure out what its final velocity is, because its final velocity is going to be equal to 9.80 meters per second squared times 1.2 seconds. So its velocity in the y direction is going to be equal to 9.8 times 1.2 11.76 meters per second in the negative direction. And I'm going to keep 1.278. So 1.278 times 9.8 is actually going to be 12.5. So I had a significant figure problem. I didn't keep enough significant figures here, so that changed my answer, 1.278 meters seconds. So always be careful about that. I carried an incorrect amount of significant figures, and it changed my velocity significantly because acceleration of gravity is large. So now I have my y component of my velocity. My x component of velocity, oh look, I gave it to you. So v naught x is going to equal 10 meters per second. And another thing that we're going to do is we're going to take a look at the overall position. Right, the overall position is going to be that times the time. The time that it takes to hit the ground is the time that it takes to cover this distance. So that means that the relationship between the horizontal and the vertical axis is actually time. So the time is going to be 1.278 seconds. So that makes the position 12.78 meters because the velocity was 10 meters per second. Now, I have the final position. I have Vy equals negative 12.52 meters per second. I have the Vx equals 10.0 meters per second. So my resultant velocity at that point in time, 1.278 seconds after it leaves, is going to be the vectorial addition of 12.52 and 10 meters per second. So it's going to be 12.52 squared plus 10.0 squared. Which is 16.0 meters per second. That's the resultant velocity right here. And we need to know what that angle is. And the angle is going to be tangent theta. And that's going to be Vy over Vx, or 12.52 over 10. And that's going to be 51 degrees, and that was a negative 12.52, so that means that 51 degrees is below the horizon, or down below that x position. So it's 16.0 meters per second at 51 degrees below the horizon, or below x. And the resultant velocity, you know that the answer here could be plus or minus for these values, and you know that the velocity vector is pointing down below, so you could give that a negative value, but you don't need to give it a negative value because this angle right here below the horizon gives you everything that you need to know. And so that's one example of how we can use these relationships to solve for a projectile motion problem. And these relationships are actually going to be incredibly useful for us as we progress in this class to take a look at those. So that's our introduction and overview of taking a look at projectile motion. There's one more section, part 3 of 3.5, that we'll cover, and then that's going to leave us with the range equations and getting set up for our projectile motion activities.